Hi everybody, welcome back to another Engsci recap video. My name is Jason. I just finished my second year of engineering science at the University of Toronto. And it's been a while since I've recorded one of these videos, but I figured now that the term is over, I should get back to recording them before I fall too far behind. And, another year and a lot more courses to cover. But today we'll go back to one of my first year classes and I'm going to talk about ESC190, computer algorithms and data structures. So ESC190 is a course I took in my winter term of first year, and at the time the instructor was Professor Michael Guerzhoy. So as the name of this course would suggest, it was very heavy in programming. So we did most of the programming in C, but we also used Python. Because this is our first introduction to C, we learned about pointers, functions, arrays, strings, structs, typedef, const, and some lower level ideas like the memory model and malloc. Another big part of the course was data structures. So we learned about linked lists, queues, priority queues, graphs, binary trees, hash maps, ABL trees, and a little bit of Python classes. Um, and then we learned how to apply various algorithms to these data structures. So this includes heapify and heap sort, DFS and BFS, which are search algorithms, A star and Dijkstra's algorithms. We also learned about dynamic programming, and at the end of the term, we had a little bit of fun with gradient descent and backpropagation. So today I'll be going over a problem from the final exam I wrote on April 20th, 2021. It was the final question of the exam. It was quite involved. Um, I did not solve all of the parts of this question when I first wrote the exam, so I wanted to come back and uh, sort of talk about it a little bit. I'm going to try to give enough depth, but it's a very involved question, so I won't have time to go through all the details. But the main topics of this question include dynamic programming, path recovery, general understanding of Python lists, as well as recursion. So this is the problem, and basically what it's saying is that we have two lists, and we want to find the minimum distance between those two lists. And the distance is defined as the number of transformations that one can use to transform the first list to the second list. And these transformations can either be substituting one element for another, adding an element to the list, or removing an element from the list. And to solve this problem, we want to use dynamic programming, and we want to define a 2D array D that will allow us to find the distance between L1 up to the ith element and L2 up to the jth element. And we're also given this very useful hint at the bottom where di0 is equal to I because it takes I removals to get from L1 up to the ith element to the empty list. And it's the empty list because going up to the 0th element will just give you the empty list for L2. I know this is all very sort of abstract right now. I'll try to make this a little more concrete. But part A of the question basically asks us to write a function, construct D array, that takes in the two lists, L1 and L2, which are inputs, and it wants us to return the array D, such that Dij is the distance between L1 up to element I and L2 up to element J. So they give an example of a use case, and we want our algorithm to be of complexity O of m times n, where m is the length of L1 and n is the length of L2. This basically means that for each, we basically want to traverse each element in the array and fill it in that way. So let's just step back and think about this for a moment. So let's say we have these two lists, L1 and L2. The minimum distance between them is going to be the minimum of the following three cases. The distance between 1, 2, and 1, the distance between 1, 2, and 1, 3 plus 1, and the distance between 1, 2, 3, and 1 plus 1. And each of these cases represents a different operation. So in the first case, there's no operation being performed because we noticed that the last element in both lists is 3. And so they match. So the distance between L1 and L2 will be the same as the distance between 1, 2, and 1. This is quite intuitive. And in the second case, we have an insertion happening. The reason for this is because we've removed the final element of L1. So to get to this final configuration of 1, 2, 3, and 1, 3, we would need to add an element to L1. And to account for this, we increase the distance by 1 here. As well, in this bottom case, rather than removing an element from L1, we do that for L2, and this is considered a deletion. And again, we must account for this additional operation with the +1. Now in this case, say we have two slightly different lists, it's exactly the same logic, but instead of the final elements matching, we must perform a substitution because the final elements of L1 and L2 are not equal. So the distance between L1 and L2 would be the distance between 1, 3, and 1 plus 1 because we need to substitute 2 for 3. To recall, the goal is to figure out the minimum number of transformations that would be required to transform the list L1 to L2. And all of this background information can be found in the Algorithmic Design Manual, 2nd edition by Stephen Skina. So this is my solution for part A of the problem. It's not super well written, but the logic basically goes like this. So we start off by instantiating our array D. I just fill all the elements of the matrix with -1 to begin with. And then using the hint that's given, we can basically fill in the top row and the leftmost column of our array. So in the top row, when I is equal to 0, we just set that equal to j. And when j is equal to 0, so that would be the leftmost column, we set it equal to I. The reason for this is because, as the hint said, we are either performing insertions or deletions to get to the empty list, or to start from the empty list and to get to L2, which is why we can use this as our base case. Next, we define a variable temp, which takes on a value equal to di minus 1, j minus 1 in the case where the final element of L1 and L2 match, as we said earlier, but we add 1 if they're not equal because we need to perform a substitution. And then, as we said earlier, d at ij will be equal to the minimum of temp, as well as the value, as well as the minimum distance when we remove an element from L1 or we remove an element from L2, and we would need to add 1. This represents the cases of insertion and deletion. So what we should notice is that when we construct our array, which is basically in this block here, dij is equal to the minimum, in this minimum expression, we are only calling upon values of the array where the indices are lower. And so because we've set, we have all of our values of the array for j equals 0 and I equals 0, this will construct the array basically from the bottom up. Not like from the last row to the top row. What I mean is basically from low values of I and j to high values of I and j. We will be able to fill up the array, and then we return it. So this will give us the following output for the test case that's given, which is good. Part B asks us to write a function called mindist, which returns the length of the shortest sequences of transformations from L1 to L2. And given that we've constructed our array D, this is actually quite simple. All we need to do is return the last element of the array. which is in the bottom right corner. So here, for example, the minimum distance between L1 and L2 is simply 1. And the reason for that is because all we need to do is perform a substitution, substitute a 3 for the 2. And this is probably the most involved part of the question. Basically, the function recover path should return the shortest path between L1 and L2 via substitutions, deletions, and additions. And what the function does is it returns basically all the transformations that we have to do and the sequence of lists that goes from L1 to L2. So in order to do this, first we need to keep track of how we perform the operations. So there are probably multiple ways to solve this, but the way I did it was I rewrote uh, our D array, so the one we used dynamic programming for, to also include the minimum distance operations. So rather than storing an integer at dij, I'll store a tuple whose first element is the minimum distance to get there, and the second element is the last operation that was used to get to dij. So it can either be a match, a substitution, insertion, or a deletion. Next, because we're trying to recover the path, but we're starting essentially at the destination, we can use a recursive function to read the order of operations and then generate the sequence of lists that will show the minimum distance transformation. So this is the function for constructing our new D array using tuples. It's pretty much the same as the first part. The difference is that instead of setting values of integers, we're setting tuples. So in this case, when I is equal to 0 and j is equal to 0, that's our base case. So there's no operation associated with that. So I just put -1. I use 0 to represent a match. I use 1 to represent substitution, 2 to represent deletion, and 3 to represent insertion. Other than that, this function is pretty much exactly the same. So now we have this array. This is the same test case as in part A. If you only look at the first values in the tuples, you'll see the arrays are identical, but I've added these operations as well as the second element of the tuple. And this is the recursive function that will recover the path. And you'll see at the top, this is our base case. Basically what it's saying is if the operation is -1, which is our base case, we should just return our list of transformations because we've made it to the end of the call. However, we have if statements for every other case. So in the event of a match, a substitution, or a deletion or insertion, what happens is we essentially create another recursive call of the function, and after we perform the recursive call, we have a temporary value, and this temp value will be equal to the transformation that is created through this operation. And this value of temp we will append to out. So out is the list of transformations that one must go through to get from L1 to L2. And this function will recursively build out. As you can see, it takes in the variable out as an input to the function. So originally we'll start with an empty list, and every time the function is recursively called, it receives a new out list, and it appends a new element for every operation, and it returns it. So for example, in the substitute, we have this bit of logic, temp j-1 is equal to L2 j-1. This is the substitution happening. In the deletion, we have a delete. In insertion, we have an insert. So these are all examples of how we're modifying the list and then appending that modified list to our out. And you'll see this more visually in a second, but basically our recovered path function has two steps. We construct the D array using our tuples, as I mentioned earlier, and then we return the final list of transformations that is returned by our recursive function. And as I mentioned earlier, we begin by setting out to be an empty list. So here's an example of our function working. So let's say L1 and L2 are a perfect match, then our out list should just have one list in it, since L1 and L2 are the same. In the case of a substitution here, I included a snippet from my terminal, which basically shows how the function works. So because we're working backwards, we're going recursively. We see that first we have our base case, which is L1 is equal to 1, 2. Then our function realizes we need to perform a substitution followed by another substitution. So what's happening is this line here is our base case. And when we realize we need to perform a substitution, we perform the substitution on the temp variable, which creates this, which gives us this list 2, 2. And this is our temp variable, which we then append to our out list. So this is our out list that is returned after one call of the recursive function. And after that call has been returned, we move up to the next recursive call. This next recursive call will be another substitution. Because it's another substitution, it'll perform that substitution on the temp variable, which will create the list 2, 3. This temp variable then gets appended to our out list, which is returned, and then we print it again. So this is the final answer. And as you can see, the first list has to be L1, and the last list has to be L2. And the lists in between show how we get there. Similarly here, we have a case where there is a deletion happening. So our recursive function starts at the base case, realizes that we need to perform a deletion. So this temp variable 2, 3 is after the deletion was performed, and this gets appended to our out function. And then our recursive function realizes we have two matches, which are the 2 and 3. And because these are matches, they don't actually change our out list. So they get returned, but they don't have modifications made to them. And so this is just our final answer. For this insertion case, we start at our base case, which is 1. We perform the insertion on our temp variable, which gives us 2, 1. And we append this temp variable to our list. So we have 1, 2, 1. And then when that call of the recursive function is returned, we move up a level to the next recursive call, which says that we must do a substitution. So that substitution is performed on our temp variable, and it is appended to our list. And so we get this final output for our out variable. So I hope that somewhat made sense. I know this is a bit of a longer video, but I'd like to make some quick acknowledgements before I finish off. I'd like to thank Professor Michael Guerzhoy for the course and the final exam content, and as well as my lab TA, Yinyan, for being very patient when I slept through an office hour. But yeah, I'd also like to thank the individuals whose template I took for this presentation. And yeah, I hope you enjoyed this video, and I'll see you next time.